From a distance, our solar system looks empty. If you enclosed it within a sphere one large enough to contain the orbit of Neptune, the outermost planet, then the volume occupied by the Sun, all planets, and their moons would take up a little more than 1/1,000,000th the enclosed space. But it's not empty. The space between the planets contains all manner of chunky rocks, pebbles, ice balls, dust, streams of charged particles, and far-flung probes. The space is also permeated by monstrous gravitational and magnetic fields. Interplanetary space is so not empty that Earth, during its 30 km/s orbital journey, plows through hundreds of tons of meteors per day, most of them no larger than a grain of sand. Nearly all of them burn in Earth's upper atmosphere, slamming into the air with so much energy that the debris vaporizes on contact. Our frail species evolved under this protective blanket. Larger, golf ball-size meteors heat fast but unevenly, and often shatter into many smaller pieces before they vaporize. Still larger meteors singe their surface but otherwise make it all the way to the ground intact. You'd think that by now, after 4.6 billion trips around the Sun, Earth would have vacuumed up all possible debris in its orbital path. But things were once much worse. For 500 million years after the formation of the Sun and its planets, so much junk rained down on Earth that heat from the persistent energy of impacts rendered Earth's atmosphere hot and our crust molten. One substantial hunk of junk led to the formation of the Moon. The unexpected scarcity of iron and other higher mass elements in the Moon, derived from lunar samples returned by Apollo astronauts, indicates that the Moon most likely burst forth from Earth's iron-poor crust and mantle after a glancing collision with a wayward Mars-sized protoplanet. The orbiting debris from this encounter coalesced to form our lovely, low-density satellite. Apart from this newsworthy event, the period of heavy bombardment that Earth endured during its infancy was not unique among the planets and other large bodies of the solar system. They each sustained similar damage, with the airless, erosionless surfaces of the Moon and Mercury preserving much of the cratered record from this period. Not only is the solar system scarred by the flotsam of its formation, but nearby interplanetary space also contains rocks of all sizes that were jettisoned from Mars, the Moon, and Earth by the ground's recoil from high-speed impacts. Computer studies of meteor strikes demonstrate conclusively that surface rocks near impact zones can get thrust upward with enough speed to escape the body's gravitational tether. At the rate we are discovering meteorites on Earth whose origin is Mars, we conclude that about 1,000 tons of Martian rocks rain down on Earth each year. Perhaps the same amount reaches Earth from the Moon. In retrospect, we didn't have to go to the Moon to retrieve Moon rocks. Plenty come to us, although they were not of our choosing and we didn't yet know it during the Apollo program. Most of the solar system's asteroids live and work in the main asteroid belt, a roughly flat zone between the orbits of Mars and Jupiter. By tradition, the discoverers get to name their asteroids whatever they like. Often drawn by artists as a region of cluttered, meandering rocks in the plane of the solar system, the asteroid belt's total mass is less than 5% that of the Moon, which is itself barely more than 1% of Earth's mass. Sounds insignificant. But accumulated perturbations of their orbits continually create a deadly subset, perhaps a few thousand, whose eccentric paths intersect Earth's orbit. A simple calculation reveals that most of them will hit Earth within 100 million years. The ones larger than about a kilometer across will collide with enough energy to destabilize Earth's ecosystem and put most of Earth's land species at risk of extinction. That would be bad. Asteroids are not the only space objects that pose a risk to life on Earth. The Kuiper belt is a comet-strewn swath of circular real estate that begins just beyond the orbit of Neptune, includes Pluto, and extends perhaps as far again from Neptune as Neptune is from the Sun. The Dutch-born American astronomer Gerard Kuiper advanced the idea that in the cold depths of space, beyond the orbit of Neptune, there reside frozen leftovers from the formation of the solar system. Without a massive planet upon which to fall, most of these comets will orbit the Sun for billions more years. As is true for the asteroid belt, some objects of the Kuiper belt travel on eccentric paths that cross the orbits of other planets. Pluto and its ensemble of siblings called Plutinos cross Neptune's path around the Sun. Other Kuiper belt objects plunge all the way down to the inner solar system, crossing planetary orbits with abandon. This subset includes Halley, the most famous comet of them all. Far beyond the Kuiper belt, extending halfway to the nearest stars, lives a spherical reservoir of comets called the Oort cloud, named for Jan Oort, the Dutch astrophysicist who first deduced its existence. This zone is responsible for the long-period comets, those with orbital periods far longer than a human lifetime. Unlike Kuiper belt comets, Oort cloud comets can rain down on the inner solar system from any angle and from any direction. The two brightest of the 1990s, comets Hale-Bopp and Hyakutake, were both from the Oort cloud and are not coming back anytime soon. If we had eyes that could see magnetic fields, Jupiter would look 10 times larger than the full moon in the sky. Spacecraft that visit Jupiter must be designed to remain unaffected by this powerful force. As the English physicist Michael Faraday demonstrated in the 1800s, if you pass a wire across a magnetic field, you generate a voltage difference along the wire's length. For this reason, fast-moving metal space probes will have electrical currents induced within them. Meanwhile, these currents generate magnetic fields of their own that interact with the ambient magnetic field in ways that retard the space probe's motion. Last I had kept count, there were 56 moons among the planets in the solar system. Then I woke up one morning to learn that another dozen had been discovered around Saturn. After that incident, I decided to no longer keep track. All I care about now is whether any of them would be fun places to visit or to study. By some measures, the solar system's moons are much more fascinating than the planets they orbit. Earth's moon is about 1/400th the diameter of the Sun, but it is also 1/400th as far from us, making the Sun and the Moon the same size on the sky, a coincidence not shared by any other planet-Moon combination in the solar system, allowing for uniquely photogenic total solar eclipses. Earth has also tidally locked the Moon, leaving it with identical periods of rotation on its axis and revolution around Earth. Wherever and whenever this happens, the locked Moon shows only one face to its host planet. Jupiter's system of moons is replete with oddballs. Io, Jupiter's closest moon, is tidally locked and structurally stressed by interactions with Jupiter and with other moons, pumping enough heat into the little orb to render molten its interior rocks. Io is the most volcanically active place in the solar system. Jupiter's moon Europa has enough H2O that its heating mechanism, the same one at work on Io, has melted the subsurface ice, leaving a warmed ocean below. If ever there was a next best place to look for life, it's here. An artist co-worker of mine once asked whether alien life forms from Europa would be called Europeans. The absence of any other plausible answer forced me to say yes. Pluto's largest moon, Charon, is so big and close to Pluto that Pluto and Charon have each tidally locked the other. Their rotation periods and their periods of revolution are identical. We call this a double tidal lock, which sounds like a yet-to-be-invented wrestling hold. By convention, moons are named for Greek personalities in the life of the Greek counterpart to the Roman god after whom the planet itself was named. The classical gods led complicated social lives, so there is no shortage of characters from which to draw. The lone exception to this rule applies to the moons of Uranus, which are named for assorted protagonists in British lit. The English astronomer Sir William Herschel was the first person to discover a planet beyond those easily visible to the naked eye, and he was ready to name it after the king, under whom he faithfully served. Had Sir William succeeded, the planet list would read: Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George. Fortunately, clearer heads prevailed and the classical name Uranus was adopted some years later. But his original suggestion to name the moons after characters in William Shakespeare's plays and Alexander Pope's poems remains the tradition to this day. Among its 27 moons we find Ariel, Cordelia, Desdemona, Juliet, Ophelia, Portia, Puck, Umbriel, and Miranda. The Sun loses material from its surface at a rate of more than 1 million tons per second. We call this the solar wind, which takes the form of high-energy charged particles. Traveling up to 1,000 miles per second, these particles stream through space and are deflected by planetary magnetic fields. The particles spiral down toward the north and south magnetic poles, forcing collisions with gas molecules and leaving the atmosphere aglow with colorful aurora. The Hubble Space Telescope has spotted aurora near the poles of both Saturn and Jupiter. And on Earth, the aurora borealis and australis, the northern and southern lights, serve as intermittent reminders of how nice it is to have a protective atmosphere. Earth's atmosphere is commonly described as extending dozens of miles above Earth's surface. Satellites in low Earth orbit typically travel between 100 and 400 miles up, completing an orbit in about 90 minutes. While you can't breathe at those altitudes, some atmospheric molecules remain enough to slowly drain orbital energy from unsuspecting satellites. To combat this drag, satellites in low orbit require intermittent boosts, lest they fall back to Earth and burn up in the atmosphere. An alternative way to define the edge of our atmosphere is to ask where its density of gas molecules equals the density of gas molecules in interplanetary space. Under that definition, Earth's atmosphere extends thousands of miles. Orbiting high above this level, 23,000 miles up, 1/10 of the distance to the Moon, are the communications satellites. At this special altitude, Earth's atmosphere is not only irrelevant, but the speed of the satellite is low enough for it to require a full day to complete one revolution around Earth. With an orbit precisely matching the rotation rate of Earth, these satellites appear to hover, which make them ideal for relaying signals from one part of Earth's surface to another. Newton's laws specifically state that, while the gravity of a planet gets weaker and weaker the farther from it you travel, there is no distance where the force of gravity reaches zero. The planet Jupiter, with its mighty gravitational field, bats out of harm's way many comets that would otherwise wreak havoc on the inner solar system. Jupiter acts as a gravitational shield for Earth, a burly big brother, allowing long, 100-million-year, stretches of relative peace and quiet on Earth. Without Jupiter's protection, complex life would have a hard time becoming interestingly complex, always living at risk of extinction from a devastating impact. We have exploited the gravitational fields of planets for nearly every probe launched into space. The Cassini probe, for example, which visited Saturn, was gravitationally assisted twice by Venus, once by Earth, on a return flyby, and once by Jupiter. Like a multi-cushion billiard shot, trajectories from one planet to another are common. Our tiny probes would not otherwise have enough speed and energy from our rockets to reach their destination. I am now accountable for some of the solar system's interplanetary debris. In November 2000, the main belt asteroid 1994 Ka, discovered by David Levy and Carolyn Shoemaker, was named 13123, Tyson in my honor. While I enjoyed the distinction, there's no particular reason to get big-headed about it. Plenty of asteroids have familiar names such as Jody, Harriet, and Thomas. There are even asteroids out there named Merlin, James Bond, and Santa. Now in the hundreds of thousands, the asteroid count might soon challenge our capacity to name them. Whether or not that day arrives, I take comfort knowing that my chunk of cosmic debris is not alone as it litters the space between the planets, being joined by a long list of other chunks named for real and fictional people. I'm also glad that, at the moment, my asteroid is not headed toward Earth.